So in the last video, we were able to use group theory to determine that there are three normal modes for water, right? And that these have certain symmetries. These symmetries are, two of them are A1s, although they're different. They have different energies, even though they have the same symmetry. One is a stretch, a symmetric stretch, and one is a bend. And then there's what we call an antisymmetric stretch. By the way, for those of you who are used to organic chemistry terminology and you've learned symmetric stretch, antisymmetric stretch, etc., we're doing something, way more specific. And it's not that there's anything wrong with the terminology that is typically used when you learn infrared spectroscopy. We're just doing something more specific. And so for the kind of typical organic chemistry nomenclature, anything that's called antisymmetric, usually that means it's just not totally symmetric, right? But you can imagine, right, we can have B1 and B2 and A2 modes. Are those more or less symmetric? No, they're just different symmetries. So anyway, our way of thinking is it's just diving deeper, right? So a big question now is going back to our selection rules. We have three normal modes. Which one of these are infrared active? Which one of these will there be an intensity integral that is non-zero and thus give rise to a peak in the infrared spectrum? And recall that the answer from earlier in the chapter is only the ones with symmetry of the transition moment operator. And so you can go back to those chapters if you want to see, all the derivation of that. But basically, it ends up being very simple. And for IR spectroscopy, the transition moment operator, it's a Hamiltonian in the integral that comes from the Schrodinger equation, right, is x, y, and are the x, y, and z vectors, okay? And specifically, it's the x vector for x polarized light, a y vector for y polarized light, and the z vector for z polarized light. Now, for most IR experiments, you're going to be using non-polarized light, so you have a mixture of polarizations, and so you're blasting it with all polarizations of light. And so, but if you wanted to do a polarized experiment, which you can, and people do this quite frequently, more than you might imagine, you can get some additional information and some specificity with respect to your spectrum. But anyway, so you're just looking for ones like, okay, is anything, do any of these modes have the x, same symmetry as the x vector, B1? The answer is no. B2, though, has a symmetry of the y vector, and so that tells you that this B2 mode is IR active with y polarized light or non-polarized light, right? And the two A1 modes, those have the same symmetry as the z vector, and so they're IR active with z polarized light. So what this tells you is that in a typical IR spectrum, you will expect, if you really simplify things, and we'll go into detail a lot in this chapter, but you would expect to first order, you would basically have three peaks for these normal mode transitions. Now, because there's three different normal modes. Now, there's a lot of reasons why it's not that simple, and we'll go into that specifically for IR spectroscopy, but we'll also go deep into Raman spectroscopy as well, okay? So, you might be wondering a little bit about this polarization business. And so, not only do you need polarized light, but you need a well-oriented surface. So this means you're going to need a well-oriented sample. This means you're going to need, because otherwise, molecules are just rotating. And so their z-axis is changing constantly. And so you're just going to get an average of, random different orientations. And so you're not going to be able to distinguish between any of these different selection rules, even if you're blasting with one polarization of light, right? So you need to have a single crystal where your atoms are relatively stationary, right? Your molecules are relatively stationary. Things aren't moving around so much, so everything is well ordered, and thus you can really orient things well, okay? Or you need to put them on a surface. So there's actually a quite common, relatively common infrared technique called polarization modulation infrared absorption spectroscopy. It's a mouthful, PMM-IRIS. And this is used to detect molecules on a surface because on a surface, it uses infrared light to detect molecules specifically on a surface. So you can detect like a monolayer of molecules. So that's pretty cool. So, you know, I'm just telling you how this works basically, but you can think about this. Basically, you're going to have polarization of light and certain orientation of the molecule with the Cartesian coordinate system defined here.